Hello everyone, I'm Nogueira and today's topic is about cyclic plastic behavior of 7075 aluminium alloy. This is our presentation structure. We'll start with a brief introduction about the material, mechanical properties and its main applications, followed by the experimental procedure, results and discussion, and finally some conclusions. In a general way, the aluminium alloy can be divided in 8 series. This division is based on the second element with the highest presence. In our case, the aluminium alloy used for the study is a 7075 with heat treatment T651. It belongs to the 7000 series, so, after the aluminium, zinc is the predominant element, as shown on the first table. The second table shows the main monotonic mechanical properties of our alloy. The 7000 aluminium alloys are widely used in structural applications. In particular, the 7075 has huge importance in automotive and aeronautic sectors. We can explain this importance due to their balanced properties, such as their excellent strain-to-weight ratio, good corrosion resistance, and high toughness. To obtain an optimal design, it is important to have into consideration the load history, stress concentration effects, and the cyclic fatigue properties. To study fatigue failure, the most common cyclic loadings are constant stress range, where the cyclic load during a period is constant stress amplitude blocks, and finally, random stress range, which, like the name says, implies that there are different and random values of load. There are three main methods to obtain the cyclic stress strain curve: the single-step test, or SST, the multiple-step test, or MST, and the incremental step test, or IST. From these methods, the single-step test stands out due to its accuracy. However, this method requires more tests and is more expensive. It is also important to note that normally, during the low cycle fatigue tests, the controlled variable is the strain and not the stress. Before continuing with the experimental procedure, it's worth to review the four main objectives of the study. Its main purpose is to characterize low cycle fatigue behavior, followed by a determination of the low cycle fatigue properties, the analysis of mean stress relaxation rates, and finally, the prediction of fatigue life under variable amplitude loading. The testing machine used on the study was a Dartek with a load cell of 100 kN combined with a 12.5 mm strain gauge extensometer from Instron. Our study of the low cycle fatigue behavior of the aluminium alloy 7075 T651 took into consideration three different loading scenarios. Scenario A was performed under fully reversed strain control conditions, strain ratio R equals to -1, with strain amplitudes between 0.5% and 1.25%. Scenario B consisted in symmetrical-asymmetrical loading sequence, so, in the first stage, under fully reversed conditions, we have used strain amplitudes of 1% and 1.25%. In the second stage, with positive mean strain, strain amplitudes was 0.7% and 0.5%. The reverse was made for the scenario C. In scenarios A and B, the duration of the first stage was defined to introduce a theoretical fatigue damage equal to 20%. Tests stopped when total failure has occurred. This slide shows two typical cyclic stress strain curves for symmetrical-asymmetrical loading, test 7 on the left, and for asymmetrical-symmetrical loading, test 11 on the right. It is possible to observe that there are no significant differences between the shapes of the hysteresis loops. In both cases, we can see a softening behavior since the maximum stress reduces with increasing number of cycles. Nevertheless, the degree of cyclic strain softening is clearly different. Under fully reversed conditions, the changes of the hysteresis loops are more tenuous, either when the loading block is applied in the first stage or when the loading block is applied in the second stage of the tests. On the contrary, during the asymmetrical stages, the shape variations of the hysteresis loops are much more evident, which can be associated with mean stress relaxation phenomena. In addition, it is also clear that full relaxation is not achieved, since maximum and minimum stresses are not symmetrical due to insufficient plastic strain. As previously referred, mean stress relaxation can be explained by different phenomena. This figure compares the mean stress relaxation rates for constant amplitude loading, tests 1 and 6, symmetrical asymmetrical loading, test 8, and finally under asymmetrical symmetrical loading on test 13. Not surprisingly, in the fully reversed tests RE equals to -1, conducted at constant amplitude loading EA 0.5% and EA equals to 1.25%, mean stress remains close to zero throughout the tests. With regard to variable amplitude tests, loading sequence considerably affects the mean stress level. In test 8, the mean stress at the first stage of the loading sequence is similar to the constant amplitude of test 1, conducted at the same strain amplitude and the same strain ratio. Nevertheless, when the loading history changes, the mean stress raises and decreases rapidly towards the trajectory described by the first stage of test 13, performed at the same loading conditions. The convergence was not attained because total failure occurred. It is also evident that there is a higher mean stress relaxation rate in the second stage of test 8 than that of the first stage of test 13, which can be explained by the higher value of the mean stress registered in test 8 when loading conditions were suddenly changed. On the contrary, the comparison of the initial stage of test 8 and the second stage of test 13 shows similar values of mean stress, close to zero, and similar to those of test 1. In this study, the fatigue life predictions were done using the SWT parameter, and the fatigue properties were determined from the constant amplitude loading tests. The fatigue damage accumulation was estimated through the Miner's law. Failure occurred when damage was equal to the unity, d equals to 1. By analyzing the plot, it's possible to see the proximity between the predicted life and the experimental life, which is an interesting result. As a result of this study, it is possible to draw the following conclusions. First, regardless of the strain amplitude, it has been observed a strain softening behavior for the studied aluminium alloy. Secondly, a mean stress relaxation phenomenon has also been observed during the variable amplitude loading tests. Thirdly, the mean stress relaxation rates of the symmetrical asymmetrical sequences were higher than those of the asymmetrical symmetrical ones. And last but not least, fatigue life predictions for the variable amplitude loading scenarios were satisfactory. Thank you all for your attention.